Next, let us start exercises 2.6, and the first few are about derivatives of rational powers. Let's start with the second one. Here the function is y equal to x to the power minus 3 divided by 5, and we have to differentiate this with respect to x. So this one is pretty easy. We just straight away write the solution and where we start calculating dy dx. Because this is y and this is a rational power of x, that means where the exponent is the rational number minus 3 divided by 5, we can apply the power rule for differentiation with rational exponent. So that means this equals minus 3 divided by 5, the exponent, times x to the power that exponent minus 1. So this becomes x to the power minus 8 divided by 5. So that is the derivative. Next, let us consider number 6. Here also we have to find dy dx, and here y is minus 2 times square root of x minus 1. It is still a rational power, but it is slightly more complicated. It's not exactly x to the power 1 divided by 2, but x minus 1 to the power 1 divided by 2. So here we start the solution like this. By the scalar multiple rule and the chain rule, we have this. Let's see. So this is the given function, right? Minus 2 times the square root of x minus 1, or x minus 1 to the power 1 divided by 2. By the scalar multiple rule, first the minus 2 comes out, and then we have this. And this is where we have to apply the chain rule, because we cannot just simply differentiate this as it is. It is not exactly a power of x, but a power of x minus 1. So you see a composite function here, namely the composition of two functions. The outer function is the square root function and the inner function is x minus 1. So when you apply the chain rule, you first differentiate the outer function or outer room, we say it like that. That means the square root room with respect to what? With respect to the inner room x minus 1, keeping the inner room intact. And you already know how to do that, and that is where you again apply your derivative for rational power. So minus 2 is already here. So this 1 over 2 comes down times another power, where this time we subtract 1 from the existing exponent, which is 1 divided by 2. And because we are applying the chain rule, so we have to multiply this by the derivative of the inner room, x minus 1 with respect to x. Now after cancelling this minus 2 and 2, you get minus 1, and this one becomes minus 1 divided by 2, or 1 divided by square root of x minus 1. And this one you can clearly see will be 1, because ddx of x is 1 and ddx of 1 is 0. So this is your derivative. Next we have number 10. Here also you have to find dy dx, but it is even more complicated than the previous one. Y equals x times x square plus 1 to the power minus 1 divided by 2. Or in other words, this is x divided by square root of x square plus 1. So in this case, you understand that first of all you have to apply the product rule for differentiation, because basically it's just a product of two functions, one of which is x and the other one is this power of x square plus 1. So x times the derivative of this plus this times the derivative of x. Now it is here that we have to apply the power rule for rational exponent along with chain rule, just like we did in the previous one. So x stays, and first you differentiate the power with respect to x square plus 1. So that way you get minus 1 divided by 2, the exponent, times x square plus 1 to the power minus 1 over 2 minus 1. You subtract 1 from the exponent, and then you multiply that with the derivative of the inner room, x square plus 1 with respect to x. That is this one. Plus this one of course is very easy, ddx of x is 1, so it's just this power of x square plus 1. Now you can see that you can arrange things a little bit. You can write here minus x divided by 2 and this one will become x square plus 1 to the power minus 3 divided by 2, and the derivative of x square is 2x and the derivative of 1 is 0. So that means you multiply that with 2x plus this. Now after cancelling this 2, this is what you are left with, minus x square times x square plus 1 to the power minus 3 over 2 plus x square plus 1 to the power minus 1 over 2. If you want, you can simplify this more by say taking this common out. I am not doing those things. Okay, so this is our answer. Next, let us see number 14. Find the first derivative of this function, where you of course understand that you have to differentiate z with respect to t, because t is the independent variable here, and the function is it looks quite complicated. Z equals cosine of 1 minus 60 to the power 2 divided by 3. So you have to heavily apply the chain rule here. So we start the solution by straight away writing the derivative dz dt. Here z is the dependent variable and t is the independent variable. Now what will you do? First of all, because you have composite functions here, the outermost function is cos. So first you differentiate that, keeping the inner room intact. The derivative of cosine is minus sine. So minus sine of the inner room, 1 minus 60 to the power 2 divided by 3. Then with this you multiply the derivative of the inner room. Then also that itself is a composite function, which is a rational power. So first you do that. Inner room means which room? The 2 divided by 3th power room, using the derivative for rational function. So that way you get times 2 divided by 3 times 1 minus 60 to the power 2 divided by 3 minus 1. So here you are using the formula for the derivative of rational power, times, but you have to go inside more, because the innermost room is 1 minus 60, and then you have to multiply this entire thing with also the derivative of 1 minus 60 finally with respect to our actual independent variable t. So that's how you get this. Now let's do simplification. Minus 2 divided by 3 times, I have written this first, 2 divided by 3 minus 1 is minus 1 divided by 3 times, that means this power of 1 minus 60 times sine of this, times what is the derivative of this? 1 contributes 0 and minus 60 gives you minus 6. You already know how. So here you are getting minus 6. Now if you do cancellation and do the calculation here, minus 2 divided by 3 times minus 6 is 4. So 4 times this times sine of this, that is the derivative. Let's see another one of this type, number 18. Again find the first derivative of, this time the function is k of theta. So theta is the independent variable and it equals the 5 divided by 4th power of sine of theta plus 5. So again you have to apply chain rule 2 times. So in the solution we straight away apply the chain rule. Here you can simply write k. There is no need to write k of theta. It's understood that it is k. dk d theta is equal to, so first of all you will differentiate the outermost room, this power room, with our usual formula for rational powers, keeping the inner room intact, sine of theta plus 5. What does that mean actually? It means that you are differentiating this entire power with respect to sine of theta plus 5, as if sine of theta plus 5 itself is a variable. So 5 divided by 4 times the base to the power 5 over 4 minus 1. Same formula. Then you multiply with that the derivative of the next inner room, sine of theta plus 5 with respect to what? With respect to the room that is inside it, theta plus 5. If you had to really write this as derivative using the derivative notation, you would have written d sine theta plus 5 and below the notation, I mean below the notation means in the denominator of the notation, you would write d of theta plus 5. So that's why it is cosine of theta plus 5, and then finally you also have to multiply with another derivative, namely the derivative of the innermost room, which is theta plus 5, now finally with respect to theta. So dd theta of theta plus 5. So this one becomes, I mean, after you do a little simplification, 5 divided by 4 times cosine of theta plus 5. This one is going to be 1, so times sine of theta plus 5 to the power, what is this? 5 over 4 minus 1 is 1 divided by 4. So that is the derivative. The next heading is differentiating implicitly. So now we are going to use implicit differentiation, and let's consider number 20. Find dy dx from this relation. We are no longer given y as an explicit function of x, but we are only given this equation that x and y satisfy. X cube plus y cube is equal to 18xy. From this we have to find dy dx. We have started the solution just like that, but you already know what we did here. We differentiated both sides of this equation implicitly with respect to x. If you want, you can write that. Okay, differentiating both sides of the given equation implicitly with respect to x, we have this. So to differentiate the left hand side, first you apply the sum rule. So it becomes d dx of x cube plus d dx of y cube. That is equal to d dx of 18xy. This is your ordinary power rule. So this is 3x squared. And for this derivative, you have to apply the chain rule, assuming that y is a differentiable function of x. So first you differentiate the outer power rule, obtaining 3y squared, and then multiply that with the derivative of y with respect to x, dy dx. Here first 18 comes out. I have not shown those steps because it would make too many steps. Okay. So first 18 comes out, and then we have 18 times d dx of xy by the constant multiple rule. And after that you have to just apply the product rule. If you differentiate x keeping y intact, you get y. So that way you get 18y plus 18 times x times dy dx. Okay. And then we gather the terms having dy dx on one side and push everything to the other side. Say we decide to take this to that side. So we get 3y square minus 18x times dy dx, and we bring this to this side. 18y minus is equal to 18y minus 3x square. So now to find dy dx, we just have to divide both sides by this. And that is just this. Dy dx equals 18y minus 3x square divided by 3y square minus 18x. And here you already know that, I mean, we have seen such examples before, that you have to interpret this expression like this. You have to avoid those points x comma y for which the denominator becomes 0. Whatever function y actually is as a function of x, it will have a graph, right? In that graph, on that graph, there will be points. If you use the coordinates of those points and use this expression, then you will get dy dx at those points. That means slopes of tangents at those points. But there will be some points on the graph itself where this denominator will be 0. There actually there is no slope. That means tangent does not exist. Maybe there is a sharp corner, something goes wrong at such points. At other points, this is the expression for the slope of tangent to the graph of y as a function of x. So do you see how powerful this is? In spite of actually not knowing which function y is as a function of x, we can still find slopes of tangents to its graph at different points. Next, let's consider number 28. Here also we have to find dy dx from this equation. X is equal to sine of y. So the solution of course starts like this. We differentiate both sides of this equation with respect to x implicitly. So the left hand side becomes ddx of x and the right hand side is ddx of sin y. ddx of x of course is 1, and here you have to apply the chain rule. So first you differentiate the sine room, the outermost room. Here there are only two rooms, the outer sine room and the inner y room. So you first differentiate the outer sine room with respect to y, obtaining cosine of y, and then you multiply with that the derivative of the inner room with respect to x, dy dx. So that way you get dy dx equal to 1 divided by cos y, or dy dx equal to secant y. Next, let us consider number 32. Again we have to find dy dx, but now from this equation. Y square times cosine of 1 divided by y is equal to 2x plus 2y. So we straight away again differentiate both sides of this equation implicitly with respect to x. You will find a little difficulty differentiating the left hand side because there is no x, only expressions involving y. But anyway, because ultimately this is a product of two functions, y square and cosine of 1 divided by y, so you have to apply the product rule. So you first say differentiate y squared with respect to x, okay, not y, times cosine of 1 over y, you leave it as it is, plus then you leave y square and differentiate cosine of 1 over y with respect to x. And the right hand side is ddx of 2x plus ddx of 2y by the sum rule. Okay. Now here itself you have to apply the chain rule once, because it is y square. So first you differentiate the outer room, which is the square room, obtaining 2y, and then multiply that with the derivative of the inner room y, that is dy dx, times cosine of 1 over y, plus, now this time y square stays as such and you are differentiating cosine of 1 divided by y with respect to x. Here there are three rooms. The outermost room is cosine, inside you have another room, the reciprocal room, and inside that reciprocal room you have the y room, the original room. So I have decided to do it somewhat slowly, okay, not writing everything at once. First you differentiate the outermost room cosine with respect to 1 divided by y, obtaining minus sine of 1 divided by y, okay. And then you multiply that with the derivative of this reciprocal room, which you can also write as y to the power minus 1 with respect to x, alright. And here, so we have applied chain rule to calculate this once, and that gave us this. And then in order to calculate this further, we have to apply the chain rule once more. If we do these two steps at once, then it would look like what we did in the previous one, for example. That is equal to, it will be, I ran out of space, so let me write on that side. So what happens to the right hand side? To differentiate 2x, first you bring 2 outside by the constant multiple rule, and then ddx of x is 1, so that way you get 2. Similarly, this one becomes 2 times dy dx, alright. Now then in the next line, this one there is nothing to do here, we just have written it somewhat differently. We have written 2y times cosine of 1 over y times dy dx, minus, but you see a plus here, but do not forget that here we have a minus, so that is why minus y square times sine 1 over y times this. Now here we are again going to apply the chain rule with the outer room, the to the power minus 1 room, and the inner room, the y room. Because this is a power of y, so by the power rule for derivatives, the derivative of the outer room will be minus 1 to the power, minus 1 times y to the power minus 1 minus 1. That means y to the power minus 2 times the derivative of the inner room, that is dy dx. That is equal to 2 plus 2 dy dx. Now these two terms already have dy dx So let me bring this one also to that side. So that's how we are going to get this. And do not forget that there is a simplification here in this second term. The first term on the left hand side remains as it is. In the second term, you have or you already have a minus, but here you are again having minus 1. So that is why plus. This power and this power of y cancel out, leaving you with only sine 1 divided by y times dy dx. Minus 2 dy dx is equal to 2. So now there is only one more line to write. Actually 2 lines. If you want to spend another line taking dy dx common out, but I have not done that. I have straight away divided both sides by this, which is what you get if you take dy dx common out. 2y times cosine of 1 divided by y plus sine of 1 over y minus 2 times dy dx is equal to 2. So dy dx is this. So that's how you have the derivative.